Mansfield, who is professor at the University of Kent. She got her degree in the early 90s at the University of Sydney and came to the UK in 1995 and has been here ever since. She's a fellow of the Institute of Mathematics and its Applications and the author of a very, very excellent book, which was published either in 2010 or 2012, depending on who you believe. I believe her. There it is. So, without further ado, please.
Thank you, Rob. Thank you. So I'm very happy to be here. Can you all hear me? Yep, great. So I was asked to give a public lecture at the University of Kent, and this is that lecture, and I'm really pleased that I can be here and have it filmed. And it is genuinely a public lecture, so there will be some parts that maybe are not appropriate for this audience, but I don't really care, because it's being filmed for non-experts. And the idea of the talk came to me as a whole. So I wanted to give a public lecture which was joyful, and this is that lecture. So that's meant to be me and all the stuff in my head. And my big problem with teaching mathematics is that telepathy doesn't work. And I just wish that it did. Anyway, so I have 7 levels of mathematical joy, at least so far. And I want to explain these in terms of my mathematical travels. And in this particular case, this really was a holiday with my husband. My husband is a mathematician, and he he likes to play on his computer with these polynomials. These polynomials arise in his field of expertise. So I would go for a long walk, and I would come back, and I would find him very frustrated because his ideas working on these polynomials were proving intractable. Now, this particular set of polynomials, it's a famous set, and they satisfy some remarkable relations. For example, nonlinear recurrence relations and nonlinear differential equations. But nevertheless, they are polynomials. Now, for people who don't know what a polynomial is, what is this? You give me your favorite number. Let's look at number 3. You give me your favorite number. I multiply it by itself 6 times, and I put it in the basket. I then multiply it by itself 3 times, and then multiply that by 20, and put it in the basket. And then I take minus 80, and I put that in the basket, and then everything in my basket I add up, and that's what that means. That's what that means, is that multiplication and addition. All right, so we're playing with these polynomials somewhere in Utah. All right, so you can see that they become very complicated and that the integers become very long. So my wonderful husband was very frustrated with his calculations, so I just suggested, why don't we plot, calculate where these polynomials evaluate to 0. So, and we can do this quite easily, but it's best done in this wonderful 2-dimensional number system known as the complex plane. Now, for the sake of people who are not mathematicians and who are genuinely from the public, what is this wonderful complex plane? It's a 2-dimensional number system. So on the red line, are all of the numbers I know and love, such as half and a third and e and pi and gamma. Not I. And I have another copy up here. So I've got 2 copies of all of the numbers that I know and like. And I say to myself, well, this is now a 2-dimensional object, and I can add them the way I normally add them, but I've got this very mysterious rule for multiplication. So it turns out that doing numbers in the 2-dimensional number plane is absolutely fabulous. This is beyond fabulous. So and I just need you to understand that it's 2-dimensional, and you can add and you can multiply. And that means I can play with my polynomials on this plane. And the fabulous theorem, the fabulous result is that if you give me a polynomial whose highest power is n, that it will achieve the value of 0 at n places, maybe with some multiplicity. Yep. So, all right. This polynomial will achieve the value 0 at 3 places on this two-dimensional plane. This one will achieve the value of 0 at 6 places on the complex plane. And we can plot them. And knowing where those zeros are is actually equivalent to knowing the polynomial. So it's equivalent set of data. And in general, these plots are just sets of dots distributed randomly on the plane. So you have to imagine we're sitting in a diner in Utah, which I believe is dry. So, but anyway, so the first one achieves the value 0 at 3 places. And I just note that 3 is 1 plus 2. This is good. This is my level of arithmetic. The next one has highest degree 6. And you can see that 6 is 1 plus 2 plus 3. So far, so good. We keep going. The next one has 10 zeros. And look, 10 is 1 plus 2 plus 3 plus 4. So at this point, we're starting to see a theme. So we keep going, and we're quite amazed. The next one has 15 zeros, and 15 is 1 plus 2 plus 3 plus 4 plus 5. And I hope you can see the theme now. This is absolutely not to be expected. It's meant to be random dots on the plane, yes, but this is far from random. This is beautiful and ordered. It's got a three-dimensional symmetry. It's really quite spectacular. So we just kept going. So here's one with 21 zeros. I'm counting for 6 numbers, and then we keep going. So now we're up to the one with 325. I skipped a few. So this one is the 25th one, and we're counting now up to 25. And I think that the next one's the last one I've got with 820 zeros. To actually write down the polynomial will probably take about 50 pages because the integers get very large. So I hope that you can see that actually these are not straight lines. They're very gently curved. Yeah? So it becomes then interesting. What's the curve? What is this curve? And the other thing that mathematicians have noted is that if I take the line there and the line there, and I look at the angle between the lines, it's now not a third of a circle, it's a fifth. So this is really quite striking. It's quite remarkable. And it turns out that something that's this beautiful will attract the attention of mathematicians, and they will then prove beautiful theorems about these things. So we worked this out, and we were very happy. Now, the polynomials are used to write down solutions to physically important equations. And in particular, one of these equations is the Korteweg-de Vries equation, which is a very, very famous differential equation governing water waves, shallow water waves. And so the magic of mathematics is that if I use one of these polynomials, supposing we look at the fourth one with 10 zeros, if I use one of these polynomials to write down the solution of a water wave, which of course is evolving in time, then it turns out that my zeros also evolve in time. They move as I change time. So I've got a little animation for you to show you what happens. Which is here. Let's make it big. And let's move that off and let's go. So here we go. We've got our 10 zeros, and you can see that it's facing one way. So that's at t is very negative. I'm now going to move time forward. Yep. No, come on, go. Here we go. And they do a little dance. And then after a while, it's facing the other way. Now, of course, the quarter-vector de Vries equation is a very famous equation precisely because you see these kind of miracles. But this was a new miracle, even for quarter-vector de Vries. So this was kind of a big deal. So let me just run it again so that you can see it, and then I'll stop it at some point. And if I move it to the middle, and then somewhere around here, I hope you can see that I've gone from having a 3-fold symmetry to a 5-fold. So here's this 5-fold symmetry coming up again in the middle of this. So pentagrams are magic, and this is this is quarter-vector de Vries magic. Okay. So let's go back to this one, and yeah, alrighty. So this is my level 1 joy, which is the discovery of a striking visual pattern. So what's level 2? So level 2 is the joy of discovery of a striking conceptual pattern. Now, of course, mathematics, I view myself as a conceptual artist, and I have three nice patterns to show you. The first one is to do with the survey of Stonehenge. So now the particular what we're interested in is the precise location of this inner, what's called the triathlons, this inner curve of taller stones here. And this was worked out in this fabulous book by Anthony Johnson, who I believe is at Oxford. And most of the book is to do with examining the archaeological record to prove that the stones really are there. That where he says is the survey of stones is where they were originally before they fell over and were moved. So let's look at what he's at his scheme. First of all, you have to create a circle of, and you're only allowed to use ropes and pegs because that's all they had. Yes? So first of all, you can create a circle of 30 equidistant points. So that's around here. And then you choose one of them as you put your peg here and you start drawing the blue, you draw the blue circles with your rope and your peg. You then move to the other side and you draw these green ones, and you then move to these other red ones and you draw these red ones, and so the whole thing is that this is where those big stones are. Now, that's really, to me, that's a strikingly beautiful geometric pattern, and we can't really know why the people who built Stonehenge would do this, but I had a little theory which I will show you later. So I need you to remember this picture for later on in the talk. So the second conceptual pattern is to do with juggling. And the language of juggling is of cascades, showers, and fountains. And the particular kind of juggling that's studied mathematically is sort of like hot potato juggling. A ball comes down and you throw it. The ball comes down to the next hand and you throw it. And there's this pattern of catching and throwing. So you catch and throw in the same moment. That's why it's called hot potato. And the hands switch. So let's look at how you might visualize this mathematically. So each arc, so the black line's one ball, the dashed line is another ball, and the thin line is a third ball. So this is 3 balls being juggled, and the number is this one goes up and lands after 1 step. That's what that one means. And then this one comes up and lands after 3 steps. That's what that 3 means, and so on and so forth. So the ball comes down. In the left hand, say, you toss it to the right and you throw it. The next one comes down in the left hand, you toss it. The next one comes down in the right, you toss it. And the whole point is, what kinds of ways can you how many ways can you draw these kinds of diagrams? That's the whole point. So, and it's an amazing number of theorems concerning the possibilities for the sequence of numbers and the information that it contains. Alrighty, so that's one. Now here's the third one. And the third one is called musical tilings. So here we have at most one voice, a percussion instrument, or pitch at a time. So this is time moving across like that. And at the first one, so you could have, say, different percussion instruments. This could be a drum, a cymbal, and a cymbal, and the drum again, and then your triangle. It goes on like this. So, and the whole point is that humans don't like regularity. So the purpose of the mathematics, so these are rhythmic patterns and canons, the purpose of the mathematics is to have the most complicated thing, so that is to be able to design things, and you can see from the words written here where the mathematicians in the audience will see where the mathematics is. And the whole point is that it imposes on freedom from inner regularity. So I found a really nice one on YouTube so that you can get the idea. Here, go there. And I've got it just, so in this one of the silence is one of the voices. So it's just to give you the idea of why this is fun. Oh, no sound? Oh no! Oh no! Let's go back. Go back to. So you get the idea, I hope, that these things are a lot of fun. Now I need to get rid of this. Yeah, I've done that. Okay. So the results are all, so the mathematics here is all algebra. In fact, undergraduate algebra. So that's level 2 joy was discovering the patterns that underlie, the mathematical conceptual patterns that underlie the phenomena. But level 3 is when two apparently unrelated patterns are actually the same. So in 2016, I had a final year project student, Rachel Wyman, and she wanted to do a project on maths and music, and there are many possibilities for such projects, and she chose the tilings because she liked discrete mathematics. But at the same time, she was one of our ambassadors going into schools and doing master classes, and one of the master classes was on juggling. And she came into my office one day, she was shaking, because she'd realized that actually the two theories were the same. That you gave me a juggling pattern, I give you a musical tiling. You give me a musical tiling, I give you a juggling pattern. The juggling pattern may not be humanly possible. I think a human can juggle maybe at most 6 if you're an absolute expert. So to see why this might be so, no, that isn't what I wanted to do. I wanted to do that. Each voice, so this is time, so this is when the first ball lands, the second ball lands, the third ball lands, and each voice is a different ball. So this, we have the first ball coming down and being thrown. The second ball comes down, goes to the other thing, and then is thrown to land there, and so on and so forth. And once you see it, it's really quite clear. So, but from the outside, the language of the two applications is very different, and it's not at all clear. It wasn't obvious to begin that they were the same. Anyway, this is why mathematics is powerful and why mathematicians can be useful. Because the underlying conceptual patterns is where mathematicians live, and if the patterns are the same, then you can use whatever theorem you've got for that pattern. So after she wrote this very nice thesis explaining the rigorous correspondence between the two theories, she had a bit of fun, and she created a musical tiling version of the Wallace and Gromit theme tune and made its equivalent juggling pattern. And maybe some people here have never heard the Wallace and Gromit theme tune, so let's play you just a little bit of Wallace and Gromit from the BBC. I hope you can see. Right, I think we're done there. You can go and listen to it at your heart's content. But I think it kind of proves a point. I think it's kind of cool to have a Wallace and Gromit juggling. Okay. So level 4 joy is that, so we've seen the power of mathematics, and now we come to level 4, which is more the mystery of mathematics, and every mathematician is enraptured by some mystery. And because this is my talk, I'm telling you about what mystery enraptures me. So I don't have the photo credit for this photo, I'm sorry, if somebody knows it, can email it to me. This is a time-lapse photo of the transit of Venus across the sun. There's been 2 in the last 20 years, and I think this is from the first one. Absolutely stunning. And because it was so beautiful, I have another one. So what's the mystery? Well, the movement of planets in the heavens has been a long-term mystery to want to understand that. And of course we have Johannes Kepler, who was a data miner. Took 20 years to mine data to find his 3 laws, and these are experimental laws. So the planets, the ellipses live on a plane with the sun at a focus. They sweep out equal areas in equal times, which means that winter is slow and summer is fast. And there are other amazing things. So if you're going to have a theory of gravitation, your theory of gravitation has to find these laws. And of course it's now very famous and well known that if you formulate gravity as a least action principle, so that things are moving as geodesics, so we have this thing called a variational principle, and there's a way to do that in which you obtain what looks to be the correct laws, and you then you convert the problem to an optimization problem. So let's talk about optimization problems for a little while. We want to optimize length, so that we want the path of shortest length. We want the surface of least area. We want to have the mechanical object moves according to least energy or least work. We have curves of fastest descent, that's ski jumps. We have order waves, gravitational fields, quantum fields, and on and on and on, many, many, many. So here I've got a little video of soap films, and this is the least area containing a given curve in space. And I hope that you can see that inside there is a little another little plane of soap film. Sometimes there's a cube, sometimes there's a plane. But I've got a little video where this thing is rotated, and hopefully we can watch it for a little while. So that you can, so inside as it's rotating, you can see there's another little cube of soap film in there. Maybe it's gone now, and so on and so forth. So it is spectacular, isn't it? So the thing is that if you design a mathematical model for least area, then you have to find those physical solutions. That's what you have to find. And there are many such problems. Beehive design. So supposing you're designing a mechanical or an electronic system and you need even heating. Even heating. Then you have to find the solutions that the bees find, because they want even heating for their babies. So some of them look like like this, and some of them look like spirals. So you need your mathematical solutions to find these solutions, and here's another one, most efficient transfer. How many times should I branch to optimize the flow of nutrients and so on and so forth? So these are the kinds of optimization problems that we have that are kind of wonderful to think about. So let's go back to Newton's laws. Planetary motion is governed by those laws, and they come down to the conservation of energy and angular momentum. And we can obtain these laws, and I've put it in a black box called Noether's theorem. So just treat it as a black box. You give me a variational principle, and I then can give you these conservation laws. And these conservation laws govern reality, more or less. So what's going on here? Well, so the mystery is this. You formulate your problem mathematically. Your mathematical formulation has to be independent of the coordinate system that you're using. You have to somehow always find the results for various kinds of coordinates. So it has to be invariant under when you set the stopwatch for your experiment. That gives you conservation of energy. It has to be invariant under when you set the start line in space. That gives you conservation of momentum. And invariance under which direction you face. Conservation of angular momentum. So why does the mathematics, so these things are surely irrelevant to the actual physical object that's running the experiment. And yet, nevertheless, the invariance of your physical model under your mathematical coordinates gives you these very powerful results. And that's, to me, is a very deep mystery called Noether's theorem. So Emmy Noether published this result in what is now regarded as one of the most important papers in mathematical physics. And despite the paper, she was asked to work on it by Hilbert. Einstein knew about it. And despite the fact that she actually has the most general result available in the kind of mathematics that she had at that time, nevertheless, it was only in the 1950s, so that's 1918, was published, and we just celebrated the centenary of this paper. It was only recognised in the 50s, and only a cut-down version of her theorem. People kept discovering generalisations, but they didn't realise she already had them, even all the way to the 90s. And I think perhaps she's the only female mathematician whose work is routinely taught in undergraduate mathematics. It's her work in algebra. So her work in algebra is routinely taught. Well, certainly undergraduate algebra is very heavily influenced by her ideas. So that, to me, is another mystery. We'll come back to this later. All right. So here we have a satellite image of a cyclone. So in 1987, the UK Met Office famously failed to predict a hurricane. They famously failed to do it. And obviously this was very, very embarrassing for the Met Office. So they sent their best mathematicians to a think tank in Europe, and it came back that the numerical model did not have in it, in the number crunching, did not have a very important conservation law, one of these Noether's laws called potential vorticity, which I'm not going to talk about. But so right or wrong, I developed the idea. I mean, I was told this by the head of mathematics at the Met Office, and right or wrong, I developed the idea that I wanted to be able to embed Noether's theorem into numerical models. So I kind of started out on this great 10-year theme for my research. So we had a go, and so this is level 5 joy. Yes, we can emulate the seemingly infinitely complex in our own finite computation if you're smart enough. So this is a joy. So I wanted to show you a bit of fun using it. So I hope you've remembered Stonehenge. So with my then postdoc Tristan Pryor, who's now a reader at Bath, I wanted, let's look at the picture again. I looked at this picture and I thought it looked like some kind of diffraction grating. And I wondered what would happen if you beat a drum in the middle and looked at the acoustic waves, what would happen? Because that was my little thing that I wanted to do. And Tristan indulged my fantasy, so he actually did do it. So let's look at it. So the technical terms are shallow water equations, and we use the finite element method. There's exact energy conservation. We have weak conservation of linear and angular momentum using our method. So here we've got the three big laws all embedded in this. So this is the mesh. You can see that there's no real symmetry to the mesh. Nevertheless, I'm getting this symmetry. And this is kind of what it looks like. But let's see the animation, which is here. And let's start it. Oh, I've got to move that to there. Okay. So we're beating a drum, and we're looking at the sound waves refracting, diffracting, something, reflecting. And I hope that you can see at some point that all of the waves have come to a kind of a point which is then going to go down the avenue. So this is my fantasy, that if you had a whole bunch of drums beating in the middle of Stonehenge, it would be like a sound torch, you know, calling everybody, and people would be able to hear it from a long way away, because it had this kind of a system, was set up to maybe, who would know? I mean, they're obviously a lot smarter than we think because they built the thing. So they're clearly not stupid. Alrighty, let's go back to here. Okay. So my last two joys are quite different in character. We've all seen how sexism and other biases blighted the professional experience of Emmy Noether. And the fact is that misogyny isn't an ideology that many people claim to follow, at least not in public. And yet, nevertheless, women continue to face difficulties. And why is that so? So, the first thing is that there are two mutually reinforcing mechanisms. People draw a little line in the sand and they say, I'm good, and what's bad is out there. And then they say, well, I'm good, so I don't have to do anything. And they don't then continue to work on their own awareness, their own social awareness. They just assume they're not a bad person without understanding the mechanism behind bias. The other problem is people unthinkingly taking advantage of historical privilege without caring about who's excluded. So they just go on their lives, they think their life's working out nice, and they're not guilty of anything. And this is why we still have apparent sexism, even though people don't think they're guilty of anything. So to help you understand this, I have this nice example. It's the privilege of being able-bodied. Most people don't think about the needs for disabled people in most environments. They just they don't think of themselves as bad people, and they take advantage of the fact that most environments are built for able-bodied people. They don't worry about who's excluded. What I have observed, though, is there is an entitlement behind this taking advantage. And if you want to see naked entitlement in action, challenge somebody parked illegally in an accessible bay. And people can be amazingly aggressive. So that's what entitlement looks like. So that's what has to be overcome in order to achieve better results for women. All right, so what has this got to do with joy? Well, the thing is that in an environment where there's historical privilege and people thinking they don't need to do a great deal about anything, what we have are is level 6 joy, the joy of mentors, champions, and so so in the room we have Peter Clarkson and R.A. Isleys, and it was Peter's polynomials, and Peter's animation that you saw already. That's my dad at the left. R.A. is in the audience. I have a long-term history of being grateful to R.A. And the other one is Sir David Melville. He was a former Vice-Chancellor at my university. And I went to his office with nothing to lose. I was so miserable. I was going to walk out. And halfway through this long list of very strange things, he realised that I was possibly not working at the university he thought he was running. That my experience was different to what he thought would be the experience of his staff. So what he didn't say was, I'm not guilty and therefore you've not had your experience. What he did say was, leave it with me and I will do something. And he did. So that's why I say, if you need or want to tackle bias, don't examine your own heart. Just ask people who are affected and then act. So of course I have a lot of level 6 joy. All my colleagues, friends and fellow travellers. Eveline is here. I've known Eveline since 98. I don't know. This is Tristan on the right, who did the Stonehenge animation for me. And Gloria is a long-term participant in the program here. She's not here at the moment. And there are many. Some here, some not here, from all around the world. And what you see, of course, is that mathematical interest is everywhere. Mathematics is everywhere, and mathematical interest is everywhere. We have Germany, Hungary, Portugal, America, Spain, and Italy, and we have many more. Japan, Brazil, Russia, more Italy, more north of England, and so on. Phil Broadbridge. Phil Broadbridge is on the left, top left. This is Reinhard Quisable, who's one of the organisers of our geometry program. Phil Broadbridge was responsible for me meeting my husband. He invited him to Australia. And recently we went to a party to celebrate his birthday, or maybe his retirement, I can't remember. And Nalini, this is Nalini Joshi, who's a professor of maths at Sydney. She invited me to speak at a workshop when Peter was in Australia. So at this party in Melbourne, Nalini and Phil Broadbridge were fighting over who was responsible for my love life. So this is Nalini came to our university to give a Hardy lecture at as a guest of the London Mathematics Society, and so on. So these are people who are very familiar to some of you. And this was a wonderful day that we had in Madrid, where we had a whole week's party for Peter's and my 60th birthday, and here we have people from all around the world and all genders. And so this is level 6 joy. It's the community. So I've come now to the last level. And level 7 can only be experienced. I can't really tell you about it. I took a photograph of a champion surfer and superimposed myself. But this is how I feel. You know, I feel like behind me is the ocean of infinite possibilities, and I'm on my surfboard waiting to catch a wave. And of course, I'm trying to get to the beach in civilization, and in mathematics that means rigorous exposition, so that there's no misinterpretation of the conceptual pattern, that anybody can come along and understand it. So of course, you know, there are many spills, and you learn to be more or less skillful at riding your surfboard and at catching good waves. Yes, this is what happens. So I've had a lifetime of level 7, but what I want my students to experience level 7. And my concern is that increasingly I feel that Too many students are arriving at university, they're tentative, they're inflexible, they're too nervous about, they're too worried about right and wrong. And I want them to play. I want them to be able to learn to surf. And I think this is an absolutely wonderful photograph that I found, and you can see they're sort of helping one another and they're having a good time. And this is, to me, there should be an element of how mathematics should feel. So there are two theories. One of them is that we over-assess. There's too many tests. And another one is that you need to have a certain level of maturity to have the confidence to play. But I think children are very good at playing. I think there should be more play. So finally, here are my 7 levels of mathematical joy. I have the beautiful visual patterns. I have the beautiful conceptual patterns. I have the 2 conceptual patterns are the same. Then we have meditation on some compelling mystery or other. So then, how to use finite computation to mirror the seemingly infinitely complex. Then there's the mathematical friends in the community. And finally, there's the process and activity of mathematics itself. And what I experience is a non-verbal mind behind the mind. I am a visual thinker, as you've probably noticed. And for me, to convert the pictures and the intuitions and the structures into rigorous expositions that's part's quite challenging. Everybody has a different step that's challenging. Anyway, I hope I've convinced you that there are 7 levels, and maybe you can think about what are your levels of mathematical joy. That's.
So this is asked that we go out and enjoy the tea and cake and talk to her and ask questions out there. So yeah. Thank you again.
You're welcome.